Let me look into this crystal ball and tell your future. Not really crystal. Or shall we drink out of the fine crystallite, no, darling? This word crystal used to confuse me a lot because it got used in a lot of different contexts, like crystal balls and drinking from the fine crystal. So I'm going to ask you today to start with your science journal and write down a question. And I want you to pause for a minute and think about it and then answer it to the best of your ability. And that question is, what makes something crystal? What is the word crystal actually about? And any answer, as usual, this is your prior knowledge, so any answer that you can think of is fine. So welcome back. I hope you just paused it. And now let's talk about this idea of crystals. And what's surprising is we're going to find that some of the things that we call crystal actually are the least crystal of crystalness. So if you can get at your vocab word right now list, we're going to write down this idea of crystal structure, because when we're talking about crystal in geology, there's a specific meaning that it has. Now, these are proper crystals for sure. I suppose if you were to take quartz and carve it into a ball shape, then you could get away with calling that a crystal ball. And let me tell you why. So we know that this is a really beautiful specimen of quartz crystals. They're actually called amethyst because they've got a purple tinge to them. There's some trace element in it that makes it that purple color. Anytime you have colored quartz, it's some kind of trace mineral that does that. So what is it that makes them shaped so beautifully by nature? Well, it has to do with their crystal structure. So if you can say that, great. So crystal structure is the geometric three-dimensional arrangement of particles in a solid. So if we look at this example right here of quartz, this is, that's interesting. It's not really showing us the So here we have quartz, and here is its three-dimensional arrangement of atoms. And you can see that quartz has a composition of SiO2, and it's made out of silicon atoms and oxygen atoms. And what that tells us, the SiO2 tells us that for every one silicon atom, there's a ratio of 2 oxygen atoms. So if we were to look at a single unit cell, you would expect it to be one. So let's see them both. This actually looks like it's showing 1 to 4, but that's not actually accurate because there's more silicon atoms for each one of these oxygen atoms. But this is what like a single molecule of silicon might look like, even though it doesn't really look like that. Because what it really does is it expands and expands and expands. And that is what makes it a crystal, is that it's the structure of the atoms that actually lend shape to the outside form. And so here, let's take a look at that. Are you recognizing that shape? So what really is super cool about crystals, these that make these kind of crystals so rare, and you go ooh and ah when you see them, is that if it takes a really long time for a crystal to form, it has plenty of time, then eventually you can actually see the shape of the individual atoms' orientation to each other reflected in the outside of it. So let's quickly, let's write down some of the ideas that we just talked about. So you've got your answer here, I hope. And let's start by saying that the outside of a crystal reflects the orientation of the atoms inside the mineral. So that's an actual crystal. It's the solid structure of atoms. So ironically, just to get back to another thing that I said earlier, here's my crystal goblet. So they, rich people call their fine crystal that actually has lead in it. That's weird. but it's not crystal at all, because actually a glass is by definition something that has no crystal structure. So that's super confusing, isn't it? Yeah. So glass, not crystal. So how do crystals form? So there's a couple of things I want to, there's a couple different ways that you can form crystals. And one is through the cooling. So let's write that down. How can they form? So there's two ways. One is through the cooling of igneous rocks. As you know, igneous rocks form either deep in the earth or on the surface of the earth. This is a surface of the earth one. This is a deep in the earth one. How can I tell the difference? Well, it's because actually the crystal size. So here's a bunch of different types of igneous rocks. And you can tell how long it had to cool by whether you can see the crystals or not. And if you look close at a nice piece of granite like this, then you can see that there are individual crystals of, say, of quartz and feldspar, of pyroxene, of all of the of mica, and each one of these individual crystals. And I didn't bring my pegmatite home, the one I keep flashing in the class. I'm sorry about that. But those have really big crystals, and they're really big because they had a long time to form. They form one atom at a time over time. Now, smaller crystal grain rocks still have crystals in them, but they're so small that you can't see them with the naked eye. But you can see them if you put them under a microscope. If you take a very small slice of rock and you put it under a binocular microscope, and then you put this like neat filter on it called a polarizer, you can see the individual crystals, and they flash. They're so cool. It's like a disco ball. And all the way that they flash under this microscopic polarized light actually tells you what kind of crystal it is. Like, for example, these turquoise one, if I recall correctly, that's what it looks like, not under polarization, but those turquoise ones were mica, I'm pretty sure. And then the other thing I want you to notice is, apart from these holes in there, that they have all grown together. So that's cooling of igneous rocks. And the other way that crystals form, of course, is, as we've discussed already from last week, is particles solidifying out of solution. And this is the money. Literally, this is the money example right here, because actually where we're going with this is we're going to learn about ore minerals and such, and that is really how most of them form. So again, they form either way. No matter how they form one atom at a time, attaching to a seed. And I don't know if you recall, during the sugar lab, you had to seed your stick or your string with crystals of sugar to make sure that the crystals would grow off of that stick. And that is important too, is that you usually have to start with a seed. That's also an important idea when we get to meteorology. So watching what this looks like, this growth, if they have enough time to grow very, very slowly, eventually the crystals, you can almost see how they're kind of growing atom by atom. If you have lots of different types of crystals, they'll intermix, but you can see that the shape and structure of the crystal is going to be reflected by the shape and structure of the way the atoms attach to each other, the different orientations of atoms. And I just think this is this guy, Emmanuel Fournassiere, I don't know how you pronounce his name very well. I assume it's French. He does this beautiful photography of crystal growth. And these are all different types of crystals that you're seeing forming. Again, one atom at a time. Here's some lead crystal growing. And I'm going to actually put this link on the website so that you can see these yourself, and you can just kind of like just zone out to how cool and zen the formation of these crystals is. Oh, it's not behaving, so I'll just put that on the website for you. It's pretty cool. Again, snow is no different. So here are some liquid droplets of snow. If they become then vaporized, then gradually, and you'll see this kind of cloud of liquid droplets disappearing, and they're one by one attaching to this crystal structure of a snowflake. And it's just really quite remarkable to see how intricate this snowflake is. Snowflakes of this intricacy can only form at certain temperatures and moisture conditions. But again, this is another scientist who's really interested in the growth of crystals, who's put a few videos up there, and I can also put a link to this there for you. So your job is going to show me that you understand this concept. And we're going to go back to our good old favorite halite, which is salt. Salt is so cool because it's got such a basic and understandable cubic structure, and it's really made out of only two different elements. We've got sodium and chlorine, and sodium and chlorine exist on opposite ends of the periodic table. There's sodium, and here's chlorine over here. They're fairly close in size, but slightly different, as you can see the way they've demonstrated this. So here's the sodium in this one is the larger purple ones, because sodium is a larger, apparently, atom than chlorine, according to the way they're showing this. Wait a minute, which one is larger? I think it is the sodium, right? I'm not fussed about it. And what you have is basically a chlorine, a sodium, a chlorine. Every sodium is surrounded by chlorines, and every chlorine is surrounded by sodiums, and they bond, in this case, 4 times with each other, and so they're attached to each other. And so what I'd like you to do now is to model. Show me a model. Actually, I want you to show somebody else your model too, and you have a lot of options. First of all, you can draw it, but remember it's a 3D thing, so if you can draw it to the best of your ability in 3D, that's terrific, and you can just use this virtual museum link to draw your example. That's fine. And there are different ways you can show it. You don't have to show the bonds. The actual bonds, remember, are kind of an idea. If we were in class, I would be passing out marshmallows right now of different sizes, and we would be attaching the marshmallows to each other so that every marshmallow, like the ones in the middle here, is going to be bonded 4 times with a marshmallow of a different type. And so if you have marshmallows of 2 sizes or of even just 1 size, that's okay. I'd like to see you try and make a 3D model. And you can use cotton balls and glue if you want to. You can use toothpicks like I did. You can use clay. You can even make Play-Doh if you want to. And again, if you just want to draw a picture, that's fine too. And then there's something that I need you to do, and that's to share your creation, ideally with another Kennebec student. So if you have a Kennebec student that you can connect to, or if you want to do a Google Meet with a few Kennebec students, let's do that. And share what we've done and kind of explain how it shows the crystal structure of salt. And if you can't reach out to another Kennebec member, that's not your cup of tea, then find a family member and show them what's going on. And then I'd like you to take a picture of it and hand that in to Empower. And that'll be your assessment to finalize our learning goal, which we started last year, and that's to develop models to describe the atomic composition of simple molecules. And here we go. This is the extended structures piece. And last year, many of you were on pace by doing your glucose. Oops, this is kind of a broken up glucose. And this year, we're going to do it with a mineral structure, which is an extended structure. So, thanks. Look forward to seeing it.